I must thank colleague Mikuláš. I've made an error when publishing the second assignment. The second assignment is due on April 12th, so there is still 2 weeks, but oh no, 12 April, May, not April, and exactly 12 April wouldn't be very good. Yes, this should be yes. We are here, so in 2 weeks, 2nd of May. Yes, correct deadline. Yes, 30 days. This should be the correct time. Okay. And today I would like to complete the part on ensemble methods. What we already did was bootstrapping, and last week it was boosting. Bootstrapping means that we bootstrap the training set, so we create many new training set by randomly sampling the training set, build a classifier for each of these, and then we let them vote, or in case when we compute regression, we don't vote, we compute average. For the boosting, which was covered last week, we built one classifier. After that, we evaluate the errors, and for the instances for which there were wrong answer, we increase their weights, and we train a new classifier respecting also the weights. So we increase probability for such samples, and we combine the first and the second classifier. And we can continue recursively further. So after the second classifier, we can train the third classifier, which will emphasize weight for the wrongly classified examples. So the next classifier is built on top of the previous ones. We have shown how to do that. And at the end there was an example, small example, that if we use very weak learner with some mathematical assumptions of its properties, we can always find something which is better than the weak learner, and by combining such weak learners we can obtain quite good learner. Here it was that we started with so-called stubs. Stubs are decision trees with just one internal node and followed immediately by leaves. So for such stub, this corresponds that we select one of the dimensions for the data, one of the attributes, and select some threshold, and everything to the left of the threshold, lower than the threshold, we classify to one class, and higher or equal the threshold we classify to the second class. And this was the working that for example, the first stub was selected, this one. Which classifies correctly all these two samples, correctly all these negative samples, but these three are classified as negative. So these are the errors. So for the next round, the probability for these samples will be increased. This was the probability distribution, and probability for the remaining observations which were classified correctly, the probability is decreased. And on top of that, we build next decision stamp, which will separate these two classes and correctly these three samples, because they have big probability, big weight. So it tries to classify them correctly. Nevertheless, it makes another 3 errors, these 3 patterns in circles. So their weights will be increased for the next round. And we build a third step. And when we combine them, we obtain correct classification. So it was just an example. And there are 2 slides summarizing the method. So the method is quite simple, easy to implement, and very flexible, because it can combine any learning algorithm. So for we need not to use just the stub, just this decision trees of height 1. We can use virtually any classifier, and we can combine them. So the AdaBoost is a method how to combine the classifier in order to obtain much stronger classifier. We don't need any metric on the data, so data features need not to be normalized. This is an issue, for example, for k-nearest neighbor classifier, where if the input is not normalized, then the attribute with bigger absolute values will have much stronger influence on the classification than the remaining attributes. That this is no problem for AdaBoost. Feature selection and fusion. So we actually don't need the feature selection. Feature selection will be done during the AdaBoost, because the important features will be selected by the algorithm itself. There are almost no parameters. There was one parameter T, and T was the number of classifiers. We stuck one on each other to obtain the final classifier. So this is maybe the only parameter. We need not to know anything exact about the weak learner employed. In order to work, we need that it is a weak learner. So it must produce some classifier with error lower than 1.5. This is necessary. Otherwise the combination will not improve it. We can prove that it is effective from the complexity point of view, and also effective from the point of view of implementation, that it's easy to implement. It can be applied on almost any program for classifications. On the other hand, we need the weak learner, and without guarantees on the weak learner, we have no guarantee that AdaBoost will work. So this is important. It can fail. It can fail if the weak classifier is too complex. So then it can fail in the sense that it will overfit the training set and not work on any new samples. Or on the other hand, if the weak classifier is too weak, then we need to combine either a huge number of classifiers, and still the result could be bad. So in the sense that the error will be still big. empirically, it was already applied on many methods, and it could a uniform noise could disturb. So disturb, I mean that the resulting classifier has some error, and it's not possible to decrease it anymore if in presence of some noise in the training set. And now the new subject for today, these are random forests. Random forests were first published by Ryman in 2001, and it actually consists of in training big number of decision trees and combining them together. But the random, so this is the forest. Forest is many trees. Random means that these decision trees should be in some sense randomly built. Randomly during the construction there will be used some random approaches, some non-deterministic approaches. And why? Because we would like to obtain independent classifiers. So the randomness is necessary there in order to obtain classifiers which are not strongly correlated. So we can start, for example, by using CRT, the classification regression T algorithm. And for building the trees, decision trees, we can use bootstrap replicates of the original data set. Bootstrap, so we derive the new training set from the original one, and this can be done similarly as for bagging. But if we have enough samples, usually prefer the way that we subsample the original training set. So we just select some of the samples from the training set. This is done because we would like to obtain non-correlated classifiers. And at each node, when we build usually decision tree, then we consider all possible attributes for a node, whether this attribute can be used for splitting the data. So for creating some query to the attribute. But in random forest, we usually select only some subsets, for example, of size m equal to square root of the possible, p is the possible set of possible attributes. And we select just square root of p candidate attributes. And then we perform the algorithm for this building decision tree only on this subset of attributes. So cutoff values. So this means that if we build binary tree, then we need some thresholds for the query on the attributes. So this is called cutoff. And for the CART algorithm, the criterion for selecting the attribute for splitting a given node is called Gini. I don't know how to pronounce it correctly in English. Gini score, which should measure impurity of the sets in the nodes of the tree, and the goal is to obtain pure subsets, so that if we go through the decision tree, we select just some subset of samples from the training set, and the goal is to obtain subset which is homogeneous, where all the samples which arrive to a given node are from only one class. And the procedure continues recursively until some finishing criterion. For example, until a node is pure, but maybe not till this. Maybe we will stop at some threshold of impurity. And what is the Gini impurity score? So the formula is below. So F is actually a set of frequencies of samples from different classes. So here we consider M classes, and Fi is the frequency, or we can interpret it this as a probability that that an element which arrives to the set belongs to class I. And here we have a sum, and Fi is the frequency for the class I, and 1 minus Fi is the frequency of the remaining classes, all remaining classes. So this can be interpreted as the probability when we randomly pick an element, and if it belongs to class I, and the second part is the complement, so the probability that it doesn't belong to class I. And we sum this for all classes. So randomly chosen element from the set would be incorrectly labeled. So if we randomly select some element from the data set, with probability Fi, it belongs to class I, and when we randomly classify it, then with probability 1 minus of Fi, it will belong to it will be classified incorrectly. So this is one interpretation, but there is also another alternative interpretation, that this is the likelihood of two samples, if we randomly select two samples, that they belong to different classes. Why it should be used? Our goal is to obtain homogeneous sets. So the probability that if we pick two samples, the probability that they belong to different classes should be as low as possible, preferably 0. And this is obtained also by manipulating the formula. So if we compute the product, so Fi times minus Fi square, and this sum can be split into sum of Fi's minus sum of Fi squared. Sum of Fi's should cover the whole set, so we obtain 1. And sum of squares remains there, and this is 1 minus sum of squares of probabilities. And square of probability, this is the probability that if we select the one element is with probability Fi, it will belong to I, and if we select another, it will belong to the same class. So, and this is complement, so it can be interpreted as probability if I select two elements, one belongs to one class and the second to some other class. So evidently, it reaches its minimum 0 when all classes fall into a single category. And as I said, when we construct the random forest, we would like to build many decision trees, but the decision trees should be independent, not correlated. So how to obtain the just independence? So on the training set, we can use bootstrapped replicates. So if we bootstrap, then these different training sets are differ in some part, and therefore it contributes to the independence of the classifiers. We can add some randomness also by adding some noise for regression, or flipping some labels for the prediction. What does it mean? We will destroy our classifiers? No, we will flip just some small part of the outputs, and the goal is to obtain robust classification. On a split, we instead of considering all possible features, we select as best splits, and out of them we select randomly one. So not necessarily the best one. On feature selection, we select only subset of features, and only these are considered for selecting the attribute for splitting. On subspace, the 0.4 means that each time we try to split, we are going to split a node, we randomly select only subset of features, and out of them we select the best feature. The 0.5 means that for building the whole tree, we consider just a subset of features, and the subset can be selected randomly, for example. Or on all, on each node we select 2 instances of opposite class, and we select a feature, and we select a split point at random. Actually, this is something which is a little similar to the decision stump. So we build some very small decision trees, but we build huge number of such trees. Usually for some decent task, we use several hundreds of decision trees in a random forest. So here is defined margin for a random forest. So this is the difference between average vote for true class and the highest average vote for any other class. So this means that also for the decision tree, we usually set some threshold called cutoff, for which if we arrive at some node, and the percentage of the most often class in the subset is at least, let's say, 90%. We don't continue with splitting, and we just say, okay, we will classify it to the biggest class. And by changing this cutoff, we can obtain several classifiers from one fixed decision tree. So so the difference between average vote, so what we obtain, and the class of highest average vote for any other. So what should be the cutoff to vote for any other class? So this means that we have some interval, or some interval when we select given cutoff, we obtain some performance of the classifier. If we change the cutoff, we obtain classifier with different performance. and the difference between the vote, average vote, and the for the crew class, and the difference for the threshold that we vote for other class is called margin. It can be shown that random forests do not overfit as much as when we add many trees, but they rather converge to some limiting value and to some fixed generalization error. The error is usually bound by the strength, so the expected margin, and depends inversely on their mean correlation. So this is important. So inversely mean correlation. So if we have random forests with large strength, big margin, and low correlation, that the trees are not correlated, then the classifier is generalizing good. So this explains that low correlation and large strengths explains why it could work, and it works well in practice. What do you think? What are the weak points of random forests? It's usually, if I read a paper, in the paper they also state, we have a new classifier which is much better than all the previous classifiers. And we will show it on some examples, or we will give some more or less mathematical guarantees. If there are some assumptions on the task and on the data, we obtain classifiers of some quality. But usually there are also some situations in which such classifier does not work as good. Well, what are the weak points of random forest? Yes, they can overfit, but if we use this strong randomization, then the overfitting is not so bad. There is one big problem, and this is that it's hard to interpret the result. If we have a decision tree, we can easily say the classification was to this class because this attribute has a value greater than something, this attribute is lower than threshold 2, and so on. So we can give complete explanation. But if we combine several hundreds of such trees, we cannot interpret them. So the interpretation would be because 2/3 of our decision trees decided something and ask some questions, and the rest ask different questions with different results. So it's not possible. So usually because of this voting and decision boundary for decision trees is usually some curve which depends on values, on different values for attributes. So we always obtain some function if we project that to one of the attributes, some steps. When we use the random forest, then we obtain smooth boundary between the classes. So because of this averaging. When we use this random selection of splitting variables, then even weaker variables, weaker in the sense with weaker importance, can be considered, and because of this averaging effect, they still contribute to better classification. And as I said, variable importance is the key. If we, for example, study some data, let's say expression data, then we usually have several observations at huge number of attributes. And it would be very good if we are able to select just few of the attributes and say, okay, you need not to measure several thousands of genes. You need to measure just 20 genes and you will obtain better results. So how to evaluate importance of a variable? This can be combined with random forest. For example, we can use Gini score, Gini score. Gini score means that if attribute is used as the splitting attribute in a node, it will contribute for lowering, decreasing the Gini score in the childs. So if we consider the Gini score of the parent, and then we compute the Gini score for all children and compute the weighted average of this Gini score for the children. Then when we select good attribute, then the Gini score should decrease. And we can measure in all nodes where the given attribute was applied, how big was this decrease? And, and this is called the average Gini impurity decrease. So we use the Gini criterion, and we average that through all the nodes and all the trees in the random forest. And the biggest decrease of the impurity will denote the variable with highest importance. For the bootstrapping, we know that if we bootstrap the training set, some substantial part of the training set is not selected, around 30%. So these samples are called out of bag, and we can compute accuracy of the resulting decision tree on these out-of-bag samples. So we bootstrap the training set, we build a classifier, and then out-of-bag samples, on these samples we measure the performance of the classifier, its accuracy, and and again, if we measure the accuracy of the classifier, and then we take the value for the attribute. So we have this big matrix X of observations. Out of that, we select the out-of-bag samples. It will be some subset. And for a given attribute, at first we measure performance of the classifier, then we take the attribute and the values in the corresponding row of the matrix we randomly permute. And we measure the accuracy again. If the accuracy decreases after the permutation, this means this parameter was important. If the performance doesn't decrease after permuting, then maybe this attribute was not important for the decision. So this is the other method. And it's usually done in the following way. So for each bootstrap replicate, we identify the out-of-bag some instances, we predict the class membership and accumulate the correct prediction count. So we measure the accuracy. And then for each feature, this means each column, each attribute, we permute the values of the given attribute, and we use the learned decision tree to make predictions. And again, we measure accuracy of such predictions. And then the importance of the variable j is the average difference in accuracy accuracy on the out of back samples, the permuted minus the accuracy on the non-permuted, on the original. And this can be used for eliminating attributes. So we start with computing the importance of each feature of the full data set. And then we identify, we can order the features according to the importance. And low scoring features, let's say 10 on 20 features with the lowest importance, we will remove from the data set. And then we iterate the training. So we again compute importance for each of the remaining attributes. We identify 20% of attributes with the lowest importance and remove them until we arrive some small number of features, or maybe even to some constant number. And the variables from the last iterations are the most important variables. And these can be used for building, for classifying without using the complete set of attributes. So why this permutation variable importance could work? When we permute the predictor variable, then the association between the original attribute and the target attribute is lost. And if there was some association, this should break the classifier. If there is no association, then the classifier is not influenced, and the attribute is not important. So the prediction accuracy is likely to decrease substantially if the attribute was important. It was observed in some examples, sample data sets, that the Gini impurity score can be affected by multiple testing effects. And it has been shown that it could result in some biased classifiers. For example, variables with more categories are preferred. Why? Because if we have a categorical variable and it has many possible values, then when we perform split according to such variable, we obtain smaller subsets and maybe closer to purity. So such measure will prefer such variables, and but this is not the best method how to select important variables. It is reliable when we use subsampling without replacement. So not the bootstrapping as it was in bagging, but if we select just a subset of the training set without replacement, then these training sets are more independent, and this improves the working and improves the estimates of the importance. And most important point at the end. The problem are attributes which are correlated. Let us consider such example. So we have some training set, and we have two attributes which are strongly correlated, and they influence also the final classification. So if these two are important, then during the classification, the decision tree can ask some queries concerning the first attribute or the second one, and they both seem to be important. But actually, if we leave one of them out, we still obtain training set which contains almost all original information. But if we measure the variable importance, for example, using this permutation, then we obtain the high score, high importance for both of them. So correlated variables are a problem for identifying the important variables and for reducing the number of attributes. So, so this such variable importance measures may be not reliable, and what can we do against that? So we can permute the values of the selected feature only within the intervals that result from the partitions made by all the cutoff choices in the decision tree. It's a little complicated sentence here, but the information is the following. It will be later, there will be an example on the slide, but if we build the decision tree, we ask for some of the variables whether the value is greater or equal to some threshold eta 1. Then for another variable, we ask whether its value is greater or equal to threshold C2, and so on. If we consider these thresholds, for such threshold means that if I obtain subset of observations or training samples for which this query results in true, and this query also for true, then 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 we obtain some subsets for which if we ask about importance of this variable, and if we permute just this part, the corresponding part of the values corresponding to the fixed answer to both these questions, then this variable, if we permute that, and if it influences the output, then it means yes, it has influence on the correct classification. But if we permute this and the output of the classification does not change, then for samples with these properties, this remaining, this third attribute was not important. Of course, if we permute the whole attribute, maybe for some other queries in the decision tree, there will be some subsets for which this will be changed completely, the value for the first attribute, and this will change the classification, and influences the result. And this will result in bigger importance for the attribute. So what is here is that we should permute the values only within intervals for such cutoffs. We can query the same attribute several times for different value for the threshold. And in this, we build intervals. And if we permute the values only within such intervals, then the resulting variable importance measure is better. So if variable importance really estimates the independence of a variable from the target and the other variables, not only the target and all the other variables. So the variable importance is proportional, this is the mark for, is proportional to the loss of accuracy when we permute the value of the attribute. And this can be computed in many different ways. And actually, there are many algorithms which say that they compute variable importance using permutation measure, but it is done differently. So there are slight differences in the algorithms. For example, for comparing the variable importance, we can compute so-called z-score. So we compute average loss divided by the standard deviation of the average loss. So this is some kind of standardization of the loss. Because if the variables have different ranges, then the average loss and the standard average loss, standard deviation of the average loss can change considerably. So this is some kind of normalization. But it turns out that still the z-score cannot measure the statistical significance of the feature importance. It would work if the distribution for the z-score would be normal, but it is not. In many cases, it is not normal. So we need something better. Before going to some special algorithm, this will be the last algorithm in this part, I will show you application of this computations of variable importance on the Burkholderia pseudo-Malay data we have worked in the lab. So there was built a random forest with 200 decision trees. And for the decision for this random forest, there was used 5-fold cross-validation to compute the variable importance. And here are top 10 variables with the highest importance using the decrease of J9. And in the last column, there is also the top 10 attributes based on the mean decrease of accuracy. So we use this random permutation for the attribute. What can be seen? The set of the top 10 attributes, top 10 with respect to variable importance computed by the decrease of J9, is the same as the top 10 attributes obtained by computing the mean decrease of accuracy. But their ordering is different. I try to color the names of the antigens. They call the genes, but with the same color, so it's easily spot that the ordering is different, but the set of top 10 attributes is the same. And here are also the comparison of the obtained variable importance. So using decrease of J9, we obtain this sequence from the top to from the variable with highest importance in direction of lowest importance, and bottom it's similar ordering according to the variable importance computed by the mean decrease accuracy. We can notice that the heights, so the values for the mean decrease of GINI and mean decrease of accuracy are, the relative decrease are different, relative decreases. But the overall shape of the curve is very similar. And on the left here, there is ROC curve. ROC curve. So it's on the horizontal axis, there is 1 minus specificity. So it's actually this is true positive rate, and yes, true positive rates, and on the vertical axis sensitivity, true positive divided by true positive for false negative. So this is actually false positive. I am wrong. For the sensitivity, this is the true positive rate. So true positive rate means the percentage of correctly identified positive samples out of all samples which are predicted as positive. And here we have the true positive, and this is false positive. So the goal is to obtain curve with the highest area under the curve, and here we have specificity 92, sensitivity 95, and area under the curve 0.95, and this was based on the degrees of GINI, and this is based on the degrees of accuracy. The area under the curve is the same. What is different is sensitivity. And on the leftmost column, this is density plot. What is here? These short lines here are cutoffs. So for the given cutoff, we obtain some value for density. How many values will reach the region, and this shows that yes, this was built just using the top 10 attributes, and I have not included. I have also diagram for when we use all the attributes. When we use all the attributes, then we obtain curve which is a little higher. Okay, so this was application for the data you know, and now this is the last part of this section, and this is Boruta algorithm. Boruta, as you can see on the right, top right, Boruta is a name of some god, or something like that, spirit of the forest. This was developed by some researchers from Poland, and it's the following procedure. We have our training set, and we add, for each variable, we add a copy of the variable as new attributes. These are called shadow attributes, shadow variables. So these were the original, and we add another copy, and and in the shadow variables, shadow attributes, we randomly shuffle the values of each shadow variable. So we take one column and randomly shuffle, second column randomly shuffle, and so on. All the columns are randomly shuffled. Then we build a random forest classifier and compute z-scores for all variables. So for the original attributes and also for these permuted shadow attributes. Then we find maximum z-score among shadow attributes. So for these attributes, we compute maximum z-score. Z-score should compare the decrease of gyni or decrease of accuracy, and we compute maximum z-score. Maximum z-score, what does it mean? If the maximum, so this is the best of these attributes. So this is the best of these attributes, and then for each attribute with undetermined importance, we perform. We assign a hit to every attribute that scored better than minimum z-score of shadow attribute. So out of this, we obtain the maximum z-score, and then we look at z-scores for the original attributes. And if the z-score of the original attribute is much higher than this maximal z-score obtained for the shadow variables, we say, oh, okay, this seems that this attribute was really, really important, because its importance is much better than the importance of the best shadow attribute, which was permuted, which is random. So these are the hits, and then for each attribute with undetermined importance, we perform some two-sided test of equality with the maximum z-score of shadow attribute. Then we deem the attributes which have importance significantly lower than the maximal z-score for shadow attribute, and these are denoted as unimportant and will be removed. Attributes which have importance significantly higher, we assign as the associate as the important value, important attributes, and then we have reduced set of attributes, because we reduced all the unimportant variables. And then we repeat the procedure until the importance is assigned for all the attributes, which is not significantly better than the maximum z-score for the shadowed attributes, or until we obtain some small number of attributes. Do you understand the working? So the idea is that if we look just at the decrease of accuracy after permuting the values for the attribute, and then maybe we don't consider relative value for the decrease relative with other with respect to other attributes, and maybe we will assign high variable importance for some attributes which are not so important. So this algorithm is a little more thorough because it compares shadow copies of the variables with the original correct values for the attributes. And if for the random, its shadow variables are randomized, so random, if for the random variables the z-score is high, this means that the difference between the important variables and lower importance variables is not so big. Because if we permute some value, some attribute, we still obtain good classifier. So maybe it's we cannot decide. So therefore, this a little more complicated comparison that we compute maximal z-score for the shadow attributes, and we compare the score obtained for the original attributes with this maximal z-score of the shadow variable. So the importance measure depends on the loss of accuracy, and it's computed separately for all trees and then averaged and computed the score of that. And as I said, these are the authors of the Boruta algorithm. They show that the z-score is not a good, not enough. But if it is performed in this way, the authors state that it's much better and show it in some examples. But there is no mathematical guarantee that it will work better in all cases anyway. And last two slides, I think. I have said that if we have correlated variables, then this could be a problem for computing the variable importance. And instead of permuting the whole column, so this is denoted here on the left, depicted. So if we compute if we permute the whole column, maybe we will obtain false results. But if we permute the column only by sections with respect to the other cutoffs in the during the or contained in the decision tree. So for example, here this was if the attribute z has value a, then we have several possible values for the attribute xj, and we permute just these values, only values corresponding to value a of variable z. And here we randomly permute only the values corresponding to observations where the attribute z has value b, cd, and so on. So there can be more variables. Then, of course, the decrease in the accuracy would usually be lower. When we permute the whole column, then we mix the values completely, and usually the decrease of accuracy is higher. And here is an example. We use the unconditional unconditional variable importance, then we obtain these values for the variable importance. So these vertical lines are the measures for the variable importance. So we can see we have 1, 2, 3, 4, 5 very important variables. Then we have 2, 3 a little lower important variables, and so on. But actually, this attribute, which was in the second group of importance, is correlated with attribute, so H2Y8, to attribute POL3, with this importance. And if we use the conditional variable importance, we obtain that the importance of the variable is much lower than the importance of the attribute POL3. So if it is possible, then the conditional variable importance is better than the unconditional. Actually, this doesn't solve the problem of selecting important features. This is still open problem, and the approach is how to find the most important attributes are numerous. So you can find many different approaches in the literature. This is the end of this part. Questions, comments? So it was mathematical, and it's not so bad, I hope. And the important things are the ideas that we can use. Random forests are obtaining usually very good results for the classification, but and additionally they can be used for estimating the importance of variables. But still, we have no guarantee that it's the best method. And now I will just introduce the next part. The next part are hidden Markov models. I suppose that you already have no hidden Markov models. Am I right? Hidden Markov models? Yes. Okay. How much space was devoted to hidden Markov models in some other lectures you already passed? Aha, from linguistics, and you also? So I suppose that this will be very simple for you, but nevertheless, I include this part because I know that if there are all students enrolled in the course, then there are at least several persons who don't know much about Markov models. So I would like to ask you to help me or correct me when I am speaking wrongly, because sometimes I have found that I have some errors in the slides. So today I will make an introduction, and next lecture I would like to complete the part. So I will start with the motivation. Motivation are CG islands for detecting coding segments of DNA. Then I will introduce the model, and I have some examples which are from the most usual literature, so casino examples, and then the derivation for the Markov models, and derivation for the algorithms. decoding algorithm for finding the most probable path, and then forward backward algorithm, and the last part is mainly on estimating the parameters for hidden Markov models. Okay, so if we look at DNA, then we have 4 possible bases in the in the sequence. So if we consider pairs of nucleotides, then we have 16 possible pairs. And interestingly, when the first analysis of coding sequences was done, surprisingly, it was found out that the probability of pair CG is much lower than the expected probability, because the expected probability would be approximately 1/16. But if they measured it in the coding sequence, and the probability was around 8,000 instead of the expected value of around 600. So the probability was 7 times smaller than expected. But this was the probability overall in the long sequence. And when they look into the coding sequence, they found out that in coding sequence, this probability, this frequency of CG pairs is much higher. Why? Are you both from bioinformatics? No, you not? You. So you should help us. You should help us. So the question is, why is the probability of CG much smaller than they expected? Yes, you are right. It's on the next slide. And why it is higher in the coding parts? If we have a coding sequence, coding segment of DNA, then the probability of CG is much higher. But this, you could answer it, oh, true. It's not so hard. As you said, chemically, CG pair usually tends to mutate to TC. And but if it is part of a coding sequence, then after appearing of this mutation, maybe the decoded sequence will change, and the gene will not work. So it's important to keep it, to have the code there. And therefore, in coding parts, the probability of CG is higher. And therefore, segments of DNA in which the frequency of CG pairs is much higher than in the rest of the DNA are called CG islands. And CG islands are just one of the indicators that this could be a coding sequence. It is not enough, but it's a strong indicator. So how to detect CG islands? Here I have something which is denoted as a definition of CG island. CG cannot have. So the classical definition. CG island in DNA is a sequence of lengths about 200 base pairs with C plus G content of 50% and a ratio of observed to expect number of CGs that is above 0.6. Such a definition is very rough for me. The length about 200 base pairs and CG content, C plus G content around 50%. So the composition, if I count the percentage of all these base, CG, AD, and then CG should be around 1/2, and the percentage of CGs should be above 60% of the expected value. The expected value would be 1/16, and if we have a percentage at least 6/10 of times 1/16, then we have CG island. So there are two problems. First problem is so-called discrimination problem. If we obtain a sequence, and the question is this sequence, the whole sequence, CG island? And the second problem is I have obtained a long DNA sequence, and I should identify segments in the sequence which are CG islands. Actually, we are not interested in CG islands. We are interested in coding sequences. So if I obtain a sequence, I would like to say, is this whole sequence coding some gene or not? This is the first problem. And the second problem, I have long DNA sequence, and I would like to identify sequence, subsequence which encode genes. Is the localization problem. For the discrimination problem, we can apply Markov model, and for the localization problem, hidden Markov model. And as I see it, it would be better if I start with the definition next week, and at least once I will finish in time. So let us finish for today and continue next week. So thank you for your attention and for your visits to the lecture, and see you in 1 week.